Welcome back, scholars. Today we're going to take a look at some special function families as well as a few transcendental functions. Let's get started. We'll start by looking at what are called piecewise defined functions. These are simply functions consisting of multiple pieces or separate function rules for separate intervals of the domain. A piecewise defined function uses special notation. We start by defining the function using our typical function notation f of x. Then we use a large bracket on the left. Within the bracket, each of our pieces or function rules are listed along with the domain explicitly stated that applies to each of the specific rules. The graph of a piecewise function may be continuous or it may contain discontinuities. This particular example consists of 3 pieces and it is considered discontinuous because it is not defined at the input x equals 2. Note that if we were to graph each of the pieces without their respective domain restrictions, the function would look like something over here on the right, and it would not be a function at all since each input is defined at more than one output. Like all functions, we can describe a global domain and range, as well as intervals of increase and decrease. For this function, the domain will consist of all real numbers except that discontinuity at x equals 2. The range will be -1 and all values greater than or equal to 0. The increasing, decreasing, and constant intervals are referred to as open intervals. This means that we do not include the endpoints. Note the use of parentheses on each of these intervals. Formally speaking, a function cannot be either increasing or decreasing at a turning point or at the point where it transitions from increasing to decreasing and vice versa. Absolute value functions are an example of a piecewise function. The parent function f of x equals the absolute value of x is a V-shaped graph with a vertical axis of symmetry passing through its vertex. Each branch of the function consists of a linear function with opposite slopes. An absolute value function can be rewritten as a piecewise defined function. We'll start by identifying the axis of symmetry. Now let's think of each side as a separate linear function. On the left, we have a linear function with a slope of -1. If we follow that slope down to the y-axis, we find that the y-intercept will be at -3. So in slope-intercept form, the rule will be -x minus 3. We'll define the domain as all x values less than or equal to -2, which will include the x value on the vertex. On the right, we have a linear function with a slope opposite to -1, which will be +1. The y-intercept will be +1 as well. This time, for the domain, we cannot include the vertex input x equals -2 because it's already been assigned to the other piece of the function. Remember, functions can map an input to one and only one output. Similar to quadratic functions, an absolute value function consists of a minimum or a maximum value and then continues to positive or negative infinity for its output or range. Half of the function will consist of an increasing interval, while the other half will consist of an interval where the function is decreasing. To evaluate a piecewise function at a particular input, choose the appropriate function rule based on the explicitly defined domain. To evaluate f at 0, we choose the middle rule where f of x equals x. So f at 0 equals 0. To evaluate f at -1, we choose the first rule where f of x equals 1 minus x. So f of -1 equals 1 minus -1, or just 2. To evaluate f at 2, we look at the domains and find that f of x is undefined at the input x equals 2. Exponential functions are defined by a positive constant base b with a variable power. These are not considered algebraic functions, rather they're called transcendental functions. There are a few restrictions to note for b. b cannot be negative, and we exclude the value b equals 1, which would generate a constant function. The domain is all real numbers, but the range is the open interval 0 to infinity. There are no x-intercepts on the parent function, and the y-intercept is located at 0, 1. A horizontal asymptote is located at the horizontal line y equals 0, or the x-axis. This is considered an injective function, meaning it's 1 to 1. This also means that this function has an inverse, which happens to be the logarithmic function. When b is greater than 1, this is said to be a growth function. When b is between 0 and 1, this is said to be a decay function. The general logarithmic function y equals log base b of x is defined as the inverse of the exponential function y equals b to the x. Note that b, the base of the logarithm, can range from the open interval 0 to infinity. This comes from the range of the exponential function y equals b to the x. The domain is the same, the open interval 0 to positive infinity, whereas the range is all real numbers. Note that the x-intercept this time is what the y-intercept was for the exponential function. It's located at 1, 0. The vertical asymptote, not a horizontal asymptote, but instead a vertical asymptote, is located at x equals 0. That wraps up our quick look at special function families and some of the transcendental functions. Next time, we'll look really closely at inverse functions. See you then.